Welcome calculus fans to a video on evaluating functions as power series. So in our last video we saw how power series converge. In this video we'll see how to cook up power series that represent actual functions. So we'll start with a motivating example, we'll talk about strategy in general, and then we'll talk about how to do calculus on these power series expansions. So here's an example. Recall that the geometric series a times r to the n as n goes from 0 to infinity is a times the quantity 1 plus r squared and so on, and it converges, it's equal to a over 1 minus r when r is strictly less than 1. So here we'll go ahead and have a look at a special case of this power series. That is when a is equal to 1 and r is equal to x. So in this special case, we know that our power series 1 plus x squared plus x cubed and so on, it converges and it takes the value of the function 1 over 1 minus x as long as x is less than 1 in absolute value. So in the parlance of our convergence discussion from last time, we would say that this converges on a radius r equal to 1. And just to convince you that our power series is a good representation of the function, I'll go ahead and plot some partial sums of our power series. That is, go out to the power capital N and plot the function 1 over 1 minus x using various capital N terms. So here it is with n equals 2 in blue and our function 1 over 1 minus x in black. Here's n equals 5 in blue and our function 1 over 1 minus x in black. Here's n equals 8 in blue and our function 1 over 1 minus x in black. Here's n equals 11 in blue and our function 1 over 1 minus x in black. And you can imagine as n gets larger, the partial sum of the power series is a better and better approximation of the actual function. So our general strategy for dealing with power series and functions will be the following. We'll start with the power series we know, which for the time being is just the geometric series, that special case of the geometric series. We'll either replace terms or maybe differentiate terms or integrate terms to get new functions. Okay, as we work through this, we'll keep track of the new radius of convergence in our new series. So illustrate this general strategy just with a couple examples. Here's an example. Find a power series representation for the given function 3 over 1 minus 2x and indicate the radius of convergence. So again here we'll start with our power series for 1 over 1 minus x and see what happens. Okay, we'd like to have a factor of 2x instead of a factor of x, so we'll go ahead and just replace x by 2x. In our new expression, we see that 1 over 1 minus 2x is equal to 1 plus 2x quantity squared plus 2x quantity cubed, so on. Just so long now as 2x is less than 1, we go ahead and replace x by 2x in our radius of convergence also. So the radius is x less than 1/2. Now we can find the desired function multiplying this whole expression by 3. So here's our power series representation. Of course, multiplying by 3 doesn't change the radius of convergence. And we can express this in summation formation too, as the sum n equals 0 to infinity of 3 times the quantity 2x to the n on the radius of convergence r equals 1/2. Okay, let's go ahead and have a look at another example. Here's another example. A power series representation for this function 1 over 1 plus x squared. So as you can see, this looks a little bit like our geometric series, which is again where we'll start. So starting with our geometric series, we can replace x by negative x squared. We can see that 1 over 1 plus x squared is 1 minus x squared plus x to the 4th minus x to the 6th and so on. And of course, having negative x squared in absolute value less than 1 is the same as having a radius of convergence 1. So here's a perfectly good summation notation formula for it. The sum n equals 0 to infinity of minus 1 to the n times x to the power 2n, and of course the radius of convergence is 1. One more example, let's go ahead and find a power series for this function, x over 9 minus x squared. Now you can see that this is a little bit different because it has a 9 instead of a 1 in that spot, and we'll have to deal with that accordingly with a familiar multiply-divide trick. So starting with the geometric series, we can see that 1 over 9 plus x squared is the same as 1/9 times 1 over the quantity 1 plus x squared over 9. Now replacing again x by negative x squared over 9 in our geometric series, we get the following expression, and then all that's left is to multiply through by a power of x to get the expression we'd like to have. So we can see an expression for x over 9 plus x squared, multiplying through by x. You can see the odd powers of x and then the powers of 9 and the flip-floppy term that is encapsulated by the minus 1 to the n. So the sum n equals 0 to infinity, minus 1 to the n, x to the 2n plus 1 divided by 9 to the n. And again here, the radius of convergence is 3. Okay, finally, we'll talk about doing calculus on power series. So it turns out you can integrate and differentiate power series just so long as you do them on their interval of convergence. And the rule of thumb is that integrating and differentiating power series term-wise does not change the radius of convergence, but it may change what happens at the endpoints, the interval of convergence. So we'll just illustrate that with a couple examples here. So here's the first example. Let's go ahead and have a look at the function ln of 1 plus x. So we'll start with our familiar series, the geometric series. Here we'll go ahead and replace x by negative x, and we can see that we get a power series representation for 1 over 1 plus x, which when you integrate that, we'll find that we get an expression for the natural log of 1 plus x. Now, strictly speaking, there should be a constant of integration here, so I'll go ahead and put that at the front. But we'll go ahead and integrate term-wise with respect to x to see that the log of 1 plus x is c plus x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 and so on the radius of convergence 1. Now, evaluating at x equals 0, we know that log of 1 is 0, which tells us that c has to be 0. So here's our expression for the log of 1 plus x. It's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 on the radius of convergence r equals 1. Now, as an exercise, I'll let you identify that this value actually also converges when x is equal to 1. It turns out when x is equal to 1, we get the alternating harmonic series, which is convergent. So that's how the interval of convergence might change, but the radius doesn't. So here's a perfectly good power series representation for log of 1 plus x. It's the sum n equals 1 to infinity, minus 1 to the n plus 1, x to the n divided by n. Again, here the radius of convergence is 1, and technically this series converges also at x equals 1 at one of those endpoints. Okay, go ahead and have a look at another example. Here's another example of the arctan of x. The arctan of x doesn't look a whole lot like series we've found, except for its derivative. We know that the derivative of arctan is 1 over 1 plus x squared, and we actually found that series earlier. So here's the series for 1 over 1 plus x squared, 1 minus x squared plus x to the 4th minus x to the 6th, and so on, for which we can integrate term-wise to get a series for arctan. Here's that perfectly good series for arctan. It turns out here that the constant of integration is also 1, which we can quickly represent as an infinite series using summation notation. The series for arctan of x is minus 1 to the n plus 1 times x to the 2n plus 1 that should be 2n minus 1, sorry, divided by 2n minus 1. Let me fix that. And I changed my mind again. I'm going to go ahead and represent it as a sum, but starting at 0 instead. So x to the 2n plus 1 divided by 2n plus 1 times minus 1 to the n, where n goes from 0 to infinity instead of 1 to infinity. Okay, one more example of integrating and differentiating series. Here's the series, the power series representation for 1 over 1 minus x quantity squared. As it turns out, this one's related to a derivative, so we'll go ahead and write down the derivative first, and then we'll think about differentiating a series termwise. So it turns out the derivative of our friendly geometric series with the chain rule ends up being the function in question. So we'll go ahead and start with geometric series and then differentiate termwise to find the series we want. So we can see that the series representation for 1 over 1 minus x quantity squared is going to be 1 plus 2x plus 3x squared plus 4x cubed and so forth on radius of convergence x less than 1. So we can express that succinctly as an infinite series using summation notation. The sum n equals 1 to infinity of n times x to the n minus 1, again on the radius of convergence of 1. All right, hope you've enjoyed this video on functions as power series. As we expand our ability to express more functions as power series, we'll be able to make use of this replacement technique. Thanks for attention. Have a great day, and we'll see you next time. Bye-bye.